Welcome, my dear students, in this seventh and last lecture of the chapter Integration and its Applications. In the last 6 lectures, we have studied indefinite integration, definite integration, some standard forms, and some methods of integration and examples also. Now today we are going to learn applications of integrations. There are so many applications of integrations in engineering, all branches of science, and in mathematics. Today we will learn only 2 applications: area and volume. So how to find area and volume using integration? So let's start with area. Area. Area of the region bounded by the curves y equal to fx, x-axis, and lines x equal to a and x equal to b. We will find the area of the region bounded by the curves y equal to fx, x-axis, and lines x equal to a and x equal to b. Let's understand this thing by figure. Suppose this is x-axis, this is y-axis, and this is our function y equal to fx. Okay, this is line x equal to a and this line is x equal to b. Now we want to find the area bounded by the curves y equal to fx, this x-axis, and these two lines. So we want to find the area of this part. This is the figure. If fx is greater than or equal to 0 between x equal to a and x equal to b, or if x is less than 0 between x equal to a and x equal to b, then figure will be like this. This is y equal to fx, this is line x equal to a, this line is x equal to b, and we want to find this area if fx is less or equal to 0 between x equal to a and x equal to b. So what is the formula to find the area of this region? The formula is area A equal to modulus I. And what is I? Where I equal to integration a to b fx dx. This is the formula to find the area bounded by the curve fx, x-axis, and these two lines. This or you can write this in this way also, integration a to b y dx also. Both are same. You can write fx or y, both. So this is our first case, that fx y equal to fx is greater than or equal to 0 or less or equal to 0 between x equal to a and x equal to b. Then the area bounded by the curve y equal to fx, x-axis and two lines is given by this formula. Okay, so please note down this formula in your notebook. We will use this. Now the second case is like this. Let's understand this thing by a figure. Suppose y equal to fx function intersect x-axis somewhere. This is x equal to a line, this is x equal to b line, and this function is y equal to fx, and it intersect x-axis at C0 point, suppose, and we want to find this area. So again the area bounded by the curve y equal to fx, x-axis x equal to a and x equal to b, but here the situation is different. The curve intersect x-axis at C0 between x equal to a and x equal to b. So we cannot find directly the area, but the formula is like this. Area bounded by the curve is a equal to modulus of I1 plus modulus of I2. Now what is I1 and I2? I1 equal to integration a to c, this part, only from this to this part, fx dx. And what is I2? I2 equal to integration c to b fx dx. So first of all we have to find this I1 and I2, then substitute the value here and you will get the required area. So this is the second case where the function intersect x-axis between x equal to a and x equal to b. Now the third case. Suppose we want to find the area between two curves, y equal to f1x and y equal to f2x. Suppose we want to find the area between these two curves, and suppose these two curves intersect each other at x equal to a and x equal to b. Let's understand these things by a figure. This is x-axis, this is y-axis. Suppose this is our curve y equal to f1x, and the second curve is like this. This curve is y equal to f2x, and we want to find this area between these two curves, and these curves intersect each other at x equal to a, and this point is x equal to b. Then how will you find this area? So we have method, area of the required region A is equal to modulus I, and what is I? I equal to integration a to b. This is f1x minus f2x dx. This is the formula to find the area between these two curves, intersecting curves, which intersect as x equal to a and x equal to b. So these are three cases to find the area between the curves. Now let's understand and use this formula to find the area. Our first example is find the area of the region bounded by the curve y equal to 2x square, x axis and line x equal to 5. Our question is find the area of the region bounded by the curve y equal to 2x square, x axis and line x equal to 5. So before we calculate the area, we must have to draw the figure. What is the region that we have to find the area? So how will you draw this curve? Let's understand. This is x axis, this is y axis. Now we want to draw this curve. This is actually a parabola, but how will you draw this? So take x equal to 0. If you put x equal to 0, then you will get y equal to 0. So one point is this. One point is this. Now if you take x equal to 1, then you will get y equal to 2, this point. If you take x equal to minus 1, then you also get y equal to 2. If you take x equal to 2, then y equal to 8. If you take x equal to minus 2, then also you will get y equal to 8. So this is parabola like this. Okay. Now we want to draw this line x equal to 5. Suppose somewhere here x equal to 5 is here. So let's draw x equal to 5 line. Suppose this line is x equal to 5 line. So this curve x equal to 5 line and x axis. So our region is this. We want to find the area of this region. Okay. See, this is x equal to 0, this is x equal to 5, and this is our function y equal to 2x square. So our formula is required area A equal to modulus I. And what is I? I equal to integration 0 to 5 fx dx. What is our fx? See, fx is nothing but y, and y is 2x square. Okay. So this is equal to integration 0 to 5 fx is 2x square dx. The integration of this is 2. Integration of x square is x cube divided by 3. So we will write 3 here. But this is definite integration. So we have to put the bound here 0 to 5. Okay. Now 2 by 3. Put the value 5 here. So 5 cube minus 0 cube. which is equal to 2 by 3. 5 cube is 125 minus 0. So the answer is 250 divided by 3. This is the value of I. Now the area A equal to mod I equal to mod of 250 by 3 equal to 250 divided by 3. This is our area and this is the answer. So in this way we can find the area under the curve and line and x-axis bounded by this region. Okay, so I think you all can understand this example, how we can find the area bounded by this curve, x-axis and this line. Let's understand one more example. Example number 2. Find the area of the region bounded by the curves y square equal to 4x and line x equal to 2. So again we have to draw figure this is x-axis, this is y-axis. Y square equal to 4x is also a parabola. You can take, if you take x equal to 0, then y equal to 0. So this is our first point. If you take x equal to 1, then y square equal to 4. So y equal to plus 2 or minus 2. So if you take x equal to 1, then y equal to plus 2 or minus 2. So the curve will be like this. This is our y square equal to 4x curve. Okay. Now line x equal to 2, which is perpendicular to x and passes from 1 and 2. So this is our line x equal to 2. So the area bounded by the curves this y square equal to 4x and x equal to 2. The area is this. This is the total area that we have to found. Okay. But see here, this curve is symmetric about x-axis. The upper half, area of the upper half and area of the lower half is same. So we did not need to find the area of the whole part, but we will find the area of only this part. We will find the area of only this part and then we double it so we can get the whole area. So the area A equal to 2 magnitude I, modulus I. Now what is I? What is I? I is equal to, this is 0 and this is 2. So integration 0 to 2 fx dx. But first of all we have to find the fx. What is fx? Fx is y, but here we have given y square equal to 4x. So y square equal to 4x, this implies y equal to 2 square root x. We have taken y as positive because this is in first quadrant and first quadrant x and y both are positive. So we have written this positive. Now we will take y equal to 2 square root x. So this is equal to 0 to 2. This is 2 square root x dx. This is 2 integration 0 to 2 x raised to 1 by 2 dx. Okay. Now 2. What is the integration of x raised to 1 by 2? Integration of x raised to 1 by 2 is x raised to 1 by 2 plus 1, which is 3 by 2 upon 3 by 2 from 0 to 2. This is equal to 2 goes in numerator, so 2 into 2 is 4. 4 by 3, substitute 2 here, so 2 raised to 3 by 2 minus substitute here 0, so it will 0. So this is 4 by 3, and 2 raised to 3 by 2 is nothing but 2 into square root of 2. So the answer is 8 square root 2 divided by 3. This is the value of I. We have found I. Now the area A equal to mod I equal to mod of 8 square root 2 by 3, which is same as 8 square root 2 by 3. So this is our area. I think you all can understand this, how we have find, sorry, this is 2I, so we have to multiply by 2, so the answer is 16 square root 2 divided by 3, because this is A equal to 2 mod I, so we have to write here 2 mod I, so 2 into 8 is 16 square root 2 divided by 3. So this is the area of this whole region. Okay, let's learn one more example of area. Example number 3. Find the area bounded by a circle with radius r. Find the area bounded by a circle with radius r. See here, the function is not given, but we have given that it is circle. So we should know what is the equation of circle with radius r. We all know that the standard equation of circle with radius r is x square plus y square equal to r square. The center is 0, 0 and radius is r. This is y axis, this is x axis, this is our circle, radius is r. Okay, now we want to find the area of this circle. See, this circle is symmetric about x axis and y axis both. So the area of all these 4 parts are equal. So we don't need to find the area of whole circle. We will just find the area of only this part. And then we will multiply this area by 4 and we will get the whole area. So the area of circle A equal to 4 modulus I. Now what is I? So I equal to integration. This is 0, this is r. So from 0 to r fx dx. But here again we have to find fx. Fx is y. So we have to find the value of y from this. So we have x square plus y square equal to r square. Therefore y square equal to r square minus x square, and therefore y equal to square root of r square minus x square. So fx equal to square root of r square minus x square. Now we will put this in place of fx. So I equal to integration 0 to r, fx is square root of r square minus x square dx. Okay. Now what is the integration of this? Integration of this is x by 2 square root of r square minus x square plus r square by 2 sine inverse x upon r. This is the integration of square root of r square minus x square. But here we have definite integration, so we have to put the bound 0 to r. Okay. Now substitute the value r in the place of x. So this is r by 2 square root of r square minus r square plus r square by 2 sine inverse r upon r minus, we have to put 0 by 2 into r square minus 0. This is 0, so the whole thing is 0 minus r square by 2 sine inverse 0 upon r. Sine inverse 0 upon r is 0, so sine inverse 0 is also 0, so this part is also 0. Now what is the value of this? This is equal to r by 2 into r square minus I square is 0 plus r square by 2 into sine inverse 1. This is 0, this is r square by 2, sine inverse 1 is nothing but pi by 2. So our answer is pi by 4 r square. Okay. See, A is 4 mod I and I is this. We have found the value of I. Okay, I is this. So the area of circle A equal to 4 mod I equal to 4 mod pi by 4 r square. 4 will be cancel out and the answer is pi r square. And we all know that the area of circle with radius r is pi r square, and thus we have get the area of circle. Okay, I think you all have understood this thing. Okay, so these are some examples of area. Now we will learn how to find the volume. So our second topic is volume. Okay, actually the topic is volume of solid of revolution. Volume of solid of revolution. Now what is the meaning of solid of revolution? First of all we will understand these things. Solid of revolution. Let's understand these things. Let y equal to fx be any functions between x equal to a and x equal to b. Okay. This is our x-axis, this is our y-axis, and this is function y equal to fx between a and b. Okay, now solid of revolution means rotate this function, this part or this curve about x axis, rotate this curve about x axis, so we can get like this rotation. See, so we can get like this curve or this solid. If you rotate this curve about x axis, then you will get this solid. So this is known as solid of revolution. We have get this solid by rotating the curve about x axis. Now we want to find the volume of this solid part. So what is the formula? So the formula volume V equal to pi integration a to b y square dx. This is the formula to find the volume of solid of revolution about x axis. Okay, so please note down this formula in your notebook. This is very important and we will use to solve or to find volume of solid of revolution. Okay, so please note down this. So let's solve some examples. Example number 1. Determine the volume of cylinder with base radius r and height h. Determine the volume of cylinder with base radius r and height h. मीन्स पायानी त्रिज्या r होय અને ઊંચાઈ h होय તેવા સિલિન્ડર એટલે નળાકારનું ઘનફળ શોધો. We all know that the formula of volume of cylinder is pi r square h. But let's find it or let's derive it. How to find? So we all know that what is cylinder? Cylinder is like this. This is cylinder. This radius is r and this height is h. Now how will you define this cylinder as a solid of revolution? Let's understand this thing by a figure. This is x axis, this is y axis. Draw a line parallel to x axis of length h. And height is r. Okay, this is x equal to 0, this is x equal to h. Now if we rotate this line about x axis, then we will get this curve or this solid. solid of revolution means cylinder of radius r and height h. So first of all we have to find the function this. What is this function? This function is this is a line parallel to x axis which passes through r 0r. So the formula or the equation of this line is y equal to r. Okay, now we have y equal to r and our volume V equal to pi integration 0 to h y square dx. This is equal to pi integration 0 to h y square means r square dx. This is equal to pi, r square is constant and integration of 1 is x from 0 to h. Therefore V equal to pi r square, substitute here h, so h minus 0 is nothing but h, so volume V is equal to pi r square h. Thus we have get the volume of cylinder. I think you all have understood these things. Let's do one more example of volume. Example number 2. Find the volume of a cone with base radius r and height h. Find the volume of a cone with base radius r and height h. Now let's understand this thing. This is cone, this is base radius which is r, and this is height. This height is h. We want to find the volume of this. We all know that volume of this cone is 1/3 pi r square h, but we have to prove this. So we have to find a curve. This is x axis, this is y axis. Suppose this is h. Here we have a point h, x equal to h. This is radius r. Now draw a line segment joining these 2 points. Okay, if you rotate this line about x axis, then you will get this thing. So you will get the cone of height h and radius r. This is 0 and this is h. This point is. Now first of all we have to find this function, the function of this line. So this point is 0 0. The coordinate of this is x coordinate is h and y coordinate is nothing but, see, this is r. So the equation of line passing through 0 0 and hr is given by x y 1 h r 1 0 0 1 equal to 0. Expand this, so we have x into r into 1 is r, minus 0 into 1 is 0, minus y into h into 1 is h, minus 0 into 1 is 0, plus 1 into h into 0 is 0, minus 0 into r is 0, equal to 0. So our equation is rx minus hy equal to 0. Okay, therefore y equal to r upon h x, r upon hx. This is our function or equation of this line. Okay, now we will use this to find the volume. Now we know that what is the formula to find the volume. Volume V equal to pi integration, you can see here, integration from 0 to h, 0 to h, y square dx. Okay, this is equal to pi integration 0 to h, y square is r square upon h square into x square dx is equal to pi, r square is constant, h square is constant, integration of x square is x cube by 3 from 0 to h. Okay, so this is equal to pi r square upon h square, substitute here h, so h cube by 3 minus 0 cube by 3 is 0, so this is equal to pi r square upon h square into h cube by 3. Now you can cancel out h square and h cube, so our volume V equal to 1 by 3 pi r square h. This is our answer. So this is the volume of this cone of height h and radius r. I think you all have understood these things. Okay, now let's understand one more example about volume. Find the volume of sphere of radius r. Now we want to find the volume of sphere with radius r. So let's draw the figure here. This is the circle of radius r, the radius is r. If we rotate this upper part about x-axis, then we will get the sphere. Okay, so in this way we will found the volume of sphere. Now what is the equation of this circle? Equation of this circle is x square plus y square equal to r square. This point is x equal to minus r, this point is x equal to plus r. Okay, now from this y square equal to r square minus x square. Now the volume of solid of revolution, volume V equal to pi integration minus r to plus r y square dx. But see, this is an even function, y square is even function, So you can write 2 pi integration 0 to r y square dx. Okay, now put the value of y square here. 2 pi integration 0 to r y square is r square minus x square dx. This is equal to 2 pi integration 0 to, sorry, let's do the integration. 2 pi, what is the integration of r square? R square is r square into x minus integration of x square is x cube by 3 from 0 to r. Okay, so this is equal to 2 pi, substitute r here, so r square into r is r cube minus again r here, so r cube by 3 minus, if you put 0 in place of x, so r square into 0 is 0 plus r 0 cube by 3 is 0. So this is equal to 2 pi r cube minus r cube by 3, take LCM, so 3 r cube minus r cube by 3. This is nothing but 2 pi, this is 2 r cube by 3. So the answer is 2 into 2 is 4 by 3 pi r cube. So the volume is 4 by 3 pi r cube. So the volume of sphere with radius r is 4 by 3 pi r cube. Okay, I think you all have understood these things. Now let's learn one more example. Example number 4. Find the volume of solid obtained by rotating the region bounded by x square upon a square plus y square upon b square equal to 1. If we rotate this curve about x-axis, then find the volume of solid of revolution. Now let's understand what is this curve. This curve is known as ellipse. Let's understand this thing by figure. This is x-axis, this is y-axis. The graph of this function is like this. This is A and this is B. Okay. So we have to rotate this about x-axis. So we will get this type of solid like an egg. And we want to find the volume of this. So first of all, let's find y square. So this is y square by b square equal to 1 minus x square upon a square, which is equal to a square minus x square upon a square. Therefore y square equal to b square upon a square into a square minus x square. This is our function y square. Now volume V equal to pi integration. This is minus a, this is plus a. So minus a to plus a y square dx. Now again y square is even function, so we can write 2 pi integration 0 to a y square dx. Okay, therefore V equal to 2 pi integration 0 to a, what is y square? Y square is b square upon a square into a square minus x square dx. b square upon a square is constant, so 2 pi b square upon a square, and integration of a square is a square x minus x square is x cube by 3 from 0 to a. This is equal to 2 pi b square upon a square. Now substitute a here, so you will get a cube minus a cube by 3, and if you put 0 here, then the remaining part will be 0. So this. Therefore, V volume equal to 2 pi b square upon a square into, take LCM, so 3a cube minus a cube upon 3, which is equal to 2 pi b square upon a square into 2a cube by 3. So this is 2 into 2 is 4 by 3 pi b square, a square and a square will be cancelled out, so a. So the volume of this solid of revolution is 4 by 3 pi b square a. Okay, I think you all have understood these things. Okay, I think you all have understood how to find area and volume using integration. So this is the last lecture of this chapter, integration and its application, and we have finished the chapter here. So thank you very much.